Hey guys, this is going to be that worksheet for 6.1 through 6.3, which is basically just going to be highlighting some processes that we cover in 6.1 through 6.3. So using LRAM, RRAM, MRAM, and then just finding areas underneath some curves. So yeah, let's go through it. So particle starts at x equals 0, moves along the x-axis with velocity. V of t is equal to 2t plus 1 from t is greater than 0. Where is the particle at t equals 4? And so I'm going to draw just a rough sketch of my velocity graph. So this is my velocity graph. We have a y-intercept at 1 and a slope of 2. Okay, so let's say I draw it right there. And then we want to know where the position is going to be at t equals 4. So if I'm going to find how much this particle has moved from t equals 0 to t equals 4, I'm going to accumulate the area underneath this curve for the first 4 seconds. And so basically, I just want the area underneath the curve right here, from t equals 0 to t equals 4. And so in order to do that, I can break this area that I have into, I can break it up into a rectangle and a triangle, and I can just find the area of those right there. And so first thing I want to find is what is this height right here. So at t equals 4, so this is going to become, at t equals 4, this is going to become 9. And so I know that this right here is 9. This right here is 1. Definitely not to scale, I know, but that means that the area of this rectangle is 4. So the area of this triangle, area of a triangle, is 1/2 of the base times by the height. Now the height of this triangle is not 9. That's from here to here. The height is from here to here, which would be 9 minus 1, so it's going to be 8. And then all of that is just going to come out to be 16. So the total area, so the area underneath this velocity curve from 0 to 4 is going to be 4 plus 16, which is going to give me 20. And position, so now the position of the particle, since it started at x equals 0, that was the original position, so it started at x equals 0, and it ended at position 20. So position is going to be at at 20, whatever units that is. So I guess x equals 20. A particle starts at x equals 0, moves along the x-axis, and it's given this velocity. Where is the particle at t equals 4? Approximate the area under the curve using 4 rectangles of equal width and heights. And the heights determined by the midpoints of the intervals. So this curve that we have, which is just a parabola, and for t is greater than 0, so we have a parabola that's being moved up 1 unit. So maybe it looks something like this right here. And we're going to t equals 4. So we want the area underneath this curve right here, but we're going to use 4 rectangles of equal width. And so that means each rectangle is just going to have a width of 1. Okay, and we're using the midpoints of these intervals right here. So what that means is that the midpoints of these intervals are going to be the heights of our rectangles that we're using. And our rectangles are going to look accordingly, so they'll look like that right there. So that will be the height of that rectangle, height of our rectangle right there, and then the height of our rectangle will be right there. So we're just going to find the area of these 4 rectangles. That's all we're doing to approximate. So we have to use this approximation right here because we have a curve that's not, it's curved. And so finding a geometric shape for a parabola is difficult, which is why we're using smaller rectangles to help us. And so the area is going to be equal to, so I don't really have to worry about the base of these rectangles, since the base of all these rectangles is going to be 1. So basically, I'm just going to be adding up the heights of all these rectangles. So the area is going to be v of 1/2 plus v of 3/2 plus v of 5/2 plus v of 7/2. And so if I plug all these values in here, that's how I'm going to get that. So that's going to be, so 1/2 squared plus 1 plus 3/2 squared plus 1 plus 5/2 squared plus 1 plus 7/2 squared plus 1. Okay? Honestly, you can use a calculator. Yeah, I would just go ahead and use a calculator for this right here. And then, honestly, we have 1, 1, 1, 1, so we're going to have 4 plus 1/2 squared plus 3/2 squared plus 5/2 squared plus 7/2 squared. So 0.5 squared plus 1.5 squared plus 2.5 squared plus 3.5 squared plus 4, and I got 25. That's nice. So that comes out to be 25. And so since the position started at 5, or started at 0, the accumulation of our velocity curve, under our velocity curve, is estimated to be 25. It's not actually 25, but it is our approximation. And so what we're going to say here is that the position of the particle will be at x equals 25 approximately. At t equals 4. At t equals 4. Okay. For 3, so the table shows the velocity of a model train engine moving along a track for 10 seconds. Estimate the distance traveled by the engine using 10 subintervals of length 1, so that's nice right there. So that means each base of my rectangle is going to be 1, which I don't really have to do anything for my calculations. So with LRAM and with RRAM. So for LRAM, so you can see that I have these 10 intervals. So and if I'm using LRAM, I'm going to be using all these values and all these values. I'm going to exclude the furthest most right value. So 1 times by 0, 1 times by 12, 1 times by 22. When I do this, I'm basically taking the base of the rectangle, which is 1, multiplying by the height of the rectangle. So the first rectangle is going to have a height of 0. Second rectangle is going to have a height of 12. And the last rectangle is going to have a height of 6. So we're just going to, basically, all we have to do is add up these numbers right here. That's all we're doing. We're doing 0 plus 12 plus 22 plus 10 ... plus 2 plus 6. So all of these 2 plus 6 all the way to the end. Yeah, so I'm just going to use my calculator. We're going to do 12 plus 22 plus 10 plus 5 plus 13 plus 11 plus 6 plus 2 plus 6. And I get 87. So for LRAM, it's going to be equal to 87 inches. So we're accumulating velocity that's measured in inches per second, and as I accumulate velocity in inches per second, I'm going to be left with inches. And then as for RRAM, so for RRAM, that's going to be equal to, now in this case right here, I'm going to exclude the furthest most left point and then use these 10 values that I get right here. that's not going to make a difference because the furthest most left was 0, the furthest most right is 0, so we're adding up the same value. So this is also just going to be 87 inches. So, cool. There you go. For 4, so you and a companion. What is this? We're not like sounds like we're on a mission or something. You and a companion are driving along a twisty stretch of a dirt road in a car whose speedometer works but whose odometer is broken. Yeah, you're definitely on a mission. To find out how long this particular stretch of road is, you record the car's velocity at 10 seconds, 10-second intervals. Okay, now we're less on a mission. With the results shown in the table, estimate the length of the road by average. That doesn't look like how you spell averaging. The LRAM and the RRAM sum. Averaging. Okay. Maybe. All right. So LRAM and RRAM. So we're going to average the sums there and see how long this road is. So let's do an LRAM approximation. 10-second intervals. So 10, 20, 30, 40, 50, 60. It's shown here. And we're using, for LRAM, we would be excluding this last one right here. This last Y value that we get right here. So we're going to sum up all of this right here. So LRAM is going to be equal to 44 plus 15 plus 35 plus 30 plus 44 plus 35 plus 15 plus 22 plus 35 plus 44 plus 30. And I get 349. 349. Yeah, 349 feet. Right? Okay. For RRAM, only difference here is that I'm going to exclude the furthest most left endpoint and include 35, but the furthest most left was 0. So I think all I have to do is add 35 to that. So that means that we're going to get 384 feet. Okay. 10-second intervals. Oh, sorry. I didn't multiply. I was feeling I was missing something. So I added up all these right here, but the intervals here are 10-second intervals. And so that means the base of all these equal intervals is going to be 10, unlike this one where it was 1. So I have to multiply these by 10. So that's going to be equal to 349 0 feet. I was going to say, that did not look like a lot of feet for traveling at that velocity. 384 0 feet right here for an RRAM approximation. So if we add those up together, so plus 349, we're going to get 7330 feet, but we're going to divide that by 2. And I get 366.5. Oh, wait a minute. 3490 plus 3840. Okay, divide that by 2. Not 0.5. Yeah, 3665 feet. So that's what we're saying that the length of that road is right there, or our estimation is anyways. So okay, moving on. So evaluate these integrals right here. So this integral right here, notice that these are constant. So these functions right here, so f of x is equal to 5. Let's just say that right there. That's a constant function. So if I have a constant function from -2 to 1, and I'm finding the area underneath the curve right there. That's just a rectangle. So the rectangle has a height of 5. So it has a height of 5, and then we have a interval of 3. And so this integral is going to be equal to 15. All we have to do is multiply that together. So that's going to be equal to 15. Okay, and as for the other one, so the interval length here is going to be 3. And so we have a constant of pi halves. So pi halves times by 3, that's going to be equal to 3 pi halves. So whenever you're integrating, again, integral is finding the area underneath the curve. If the function or the item here is constant, then you just have to do the value times by the length of the interval. And then, yeah, you'll have it. Okay, use the graph of the integrand in areas to evaluate the integral. So we can either graph it in Desmos, or we shouldn't take too much time to just go ahead and do a rough sketch of some of these graphs right here. So we have an x-intercept of 3, and we have a slope of 1/2. I should probably... this goes all the way to -2. So let's say that this goes to -2. This right here goes to 4. So I see a trapezoid. So I'm going to calculate this integral by just finding the area of a trapezoid, which is 1/2 of the height of the trapezoid. So trapezoids, whenever we're using... a lot of times using these curves, the trapezoid's height is just the interval. So from -2 to 4, which is going to be 6. So 1/2 of 6, and then times by the sum of the bases. So the sum of the bases is going to be, so if I plug in -2 right here, that's going to give me the output of my function. So if I plug in -2, that's going to be 3 minus 1, and so that's going to be 2. Plus, and then this right here is 4, so if I plug 4 right here, 4 divided by 2 is 2, 2 plus 3 is 5, and so that's going to be 3 times by 7, which is going to be equal to 21. So that's what that integral is equal to. Okay, and then here, I can see, again, if you need to graph these in Desmos to kind of get an idea of what they are, but that right there is just a semicircle. That's a so semicircle with a radius of 3. So a semicircle with a radius of 3. Okay. And so this right here is going to be 1/2 of pi times by r squared. So this right here is just going to be 9 pi over 2, because that's going to be the area underneath this curve right there, which is just a semicircle. So half of the area of the circle. For 9, so for this one right here, we have the absolute value function. So the absolute value function from, let's see, so absolute value functions, of course, going to be V-shaped. And we want this from -2 to 1. So basically, we're going to sum up two triangles. So this is going to be equal to 1/2 of the base times by the height. Because the base here is 2, the height is also going to be 2. So 1/2 the base times the height, plus 1/2 of the base times by the height. Base times by height right there. So that's going to be equal to 2 plus a half. So that's going to be equal to 5 halves, or 2.5. All right. So here, again, that right there is a semicircle with a radius of 1. However, we're plus 1, so that's going to be shifted up 1. So kind of similar to what we have here. In fact, I'm just going to steal this graph right here. I guess it would probably be appropriate to specify here that 3 is the radius, and this time I'm going to specify 1 as the radius. But in any case, I'm going to also move this up 1 unit. So keep that in mind. So that's going to be up 1 unit. So when I find the area underneath this curve right here, we also have this rectangle that we have to keep in mind when I'm finding the area underneath underneath that curve. And so, but it does have a base of 1. Okay, so and then I just need to find the area of a semicircle with a radius of 1, and then the rectangle with the base of 2 and a height of 1. And so this right here, the area is going to be equal to 2 because that's the area here, and then plus 1/2 of pi times by r squared. So it's going to be equal to 2 plus pi over 2, plus, not equal to. But yeah, that's going to be the area here, which is also the area of that integral right there. And then here, use your calculator to evaluate the following integrals. Hopefully I went over this in class, I'll be honest. This is the night before I'm giving the lesson, and I might forget. So hopefully I don't. But so let's go ahead and let me show you how to use your calculator. So similarly, if you guys know how to use your derivative, if you go to the math option, and you can see 8 is n derivative, but 9 is fn int, which is finite integral. So if you click that, you can see that it comes up with all the stuff that you have right there. And so we're doing the integral from 0 to 5, so we can go ahead and punch that in, 0 to 5, and then the function that we have is x over x squared plus 4. So x divided by x squared plus 4. And then I'm going to do enter, and I got 0.991. So this is equal to 0.991. Also, if you want to go back, and feel free to check all of these right here. If you want to check to see if these integrals are correct using your calculator, just keep in mind that you're going to have to get the decimal for for those ones right there. But yeah, if you want to get some practice using your calculator, and if you want to verify that your responses are correct, then you can go back through all of these and just make sure. Okay, and then for this one right here, we have, now in this case right here, we're going to build this out a little bit. So 3 plus, then we'll go into math and do our integral. Oh wait, I need to put a 2 right here before that. Will it let me? I don't know. I messed up. 3 plus 2, math, number 9. Okay, and then we have the integral from 0 to pi thirds. So from 0 to pi divided by 3. And then the function is going to be tangent of x. Make sure that your calculator is in radians. Mine is, so I get 4.386. 4.386. Okay, there you go, and that should be everything for this worksheet.